there. So this is the talk, caching, payloads, and other dark arts. And we're going to dig into it. And so the way I like to start this talk a little bit is with a number. And that number is a study that was done by Amazon in 2006, where if you increased the loading time of one of their pages by 100 milliseconds, that would reduce around sales conversion by 1%. And that doesn't sound like a big number, but back in the day in 2006, that meant 107 million per year. And today that number is closer to 3.8 billion. I'll talk a little bit about who I am. I don't work at Stripe. I actually work at a place called Small PDF. Has anyone ever heard or used Small PDF before? Hands up if that is the case. Nobody's used. And does anybody know what a PDF is? Okay, cool. We're getting somewhere. We make PDFs small. I hope that's clear in the branding exercise here, right? So my previous experience is also working in connected TV industry, so I helped also build Eurosport for the 2020 Olympics. I've worked on GCN, Discovery Plus, anything but Netflix. I've worked on monetization teams, fintech teams, the fitness stuff, the likes. I love web performance, although Mateusz in the corner will put me to shame because he's the GDE in web performance. And I love engineering leadership. I've also contributed a couple of things to Raycast, actually the official Stripe extension. Has anyone here used Raycast before? Now hands are coming up. Okay, we're getting familiarity going on. So Raycast, awesome. We need to change the room. Next time I'm in Prague, all the hands have to go up. And I'm also the co-founder of Zurich.js, and I build the Stripe community in Zurich. Cool. One more thing I want to mention. Has anyone heard of NPX? NPMX, not NPX. NPMX. So NPMX, and the reason I'm bringing it up today is it's something you should really check out because we had our alpha release of NPMX a couple of days ago, and it's a really, really cool modern browser for the NPM registry. And I'm not going to be talking about it too much today, but what I want to raise it is that it's an awesome open source community started by Daniel, Ro, Patak, and a bunch of others. We're not doing the TanStack Start talk today, but actually my one contribution to the repo is adding TanStack Start over there. And there's also a cool issue open that you guys probably as event organizers may want to get in, where we're actually trying to see if it's possible to look at your NPM registry and conferences, and via your NPM registry and what NPM packages you use, surface where your maintainers are going to be showing up at different conferences. So if I maintain an NPM package and I'm showing up at React Prague, I could go on NPMX and actually see that, oh, Faris maintains package X, he's going to be showing up at this meetup, and sort of create a connection of web across that stuff. But it's a really cool community. Just wanted to highlight that. So let's set the stage for the talk. And the stage is going to start with a super pixelated photo because I couldn't find anything better to express it. But I'm not just Swiss, I'm also Pakistani. And in Pakistan, we have wonderful roads and wonderful traffic. And Pakistan's not the only place that's tormented with this. Also India and a bunch of other places if you go to Asia. And something that's interesting is that over there, you'll see a lot of Japanese cars. You'll see Toyotas, you'll see a bunch of them. And you'll also see unmaintained roads. You'll see potholes. You'll see things that break. You'll see floods. And you'll actually see a lot of cars that have to withstand extreme conditions. Roads that were just not built for most cars to work on. Actually, most of the Japanese cars that are bought over there and used, they'll go all the way to 620,000 miles on a single car. That's incredible. But let alone that, you'll actually half the time have the wrong fuel in the car, because I'm sure there's water put in the fuel half the time, and it's like diluted. Nobody's following the service manual over there. I'm sure the right tires aren't on the cars, but the people that built the cars still had to build them in a way that could withstand every single suboptimal environment. Whereas actually, if you look at German cars, you look at your BMWs, your Mercedes, your Porsches, they're beautiful cars built for the Autobahn. But if you read the instruction manual on those cars, you have to put a specific fuel, a specific tire, a specific service interval, and if you do not follow that, it's going to explode. And so I think this is very similar to localhost versus the real world. We've all used localhost before, right? Yeah, have you ever tried sharing that link with somebody? Didn't end well, right? Anyone trying to think they can build AI apps really, really quickly and sends a localhost to somebody? It's a tough conversation to have. But localhost, we all have stable networks. And we have great bandwidth, sometimes even Ethernet connections. We're a single user in an ideal environment with super powerful MacBooks most of the time, which half of our users won't have. In the real world, we'll have high latency environments, unreliable networks, and we'll have mixed devices with throttle CPUs, partial caches, stale data, flaky APIs, you name it. Has anyone heard that caching is super easy to do? Yeah, thought so. So what's the problem statement that we're going to talk about today? The problem statement is, what challenges do developers face creating seamless user experiences due to complex data fetching and management? And the words always highlighted in yellow are particularly important to look at. But that means to ask the question, that begs to ask the question, how can we build an optimal solution in suboptimal conditions? Because I watch a lot of conference talks, and something interesting I find about them is that we always talk about how do we build something ideal. How do we build something in a very scoped environment? But what about the real world? But we have to ask the question before that, why bother doing these things? And so, of course, we want our pages to load super fast. We want them to load in this golden window of 0 to 2 seconds. That's the ideal for everyone, right? But is that the case for everyone? Not always. But let's dig a little bit more into the psychology of why these response times are interesting, or more so to look at the 3 important limits of response times from this excerpt of usability engineering, which I really recommend. And so the first limit is 0.1 seconds. And what's interesting with that is that it's associated with a user feeling that the system is reacting instantaneously. Instantaneously. You click stuff, doesn't wait, it goes to the next view, transitions, so on and so forth. If we go now to 1 second, that's the limit for a user's flow of thought. So if you're going and doing multiple clicks, you're going into an N8N type application, Zapier type application, whatever it may be, and you're dragging things along, connecting things, you generally, or even when you're typing on your keyboard, have you ever had that moment where you're typing super fast, but then it lags and it doesn't catch up, right? You forget where you are, you get discombobulated, you don't know what words you were talking about, all of a sudden, like you're in your mother tongue, you're switching to your second language, it's weird, it gets weird. So what's really important is how do we stay within this 1 second or this limit of a user's flow of thought. We never want to interrupt this because that's what starts to build frustration. And then the limit beyond that is 10 seconds for keeping a user's attention. But who really waits for 10 seconds for a website these days? Unless it's a government portal or like you need to check in for an airline, you're not waiting. If you are, booking.com's not loading, I'm going to Expedia, I'm going to Trivago, I'm going wherever else, right? Does anybody wait 10 seconds these days? We're not, yeah, there we go. With TikTok and Instagram Reels, I won't even wait 5 seconds these days. But that correlates a little bit with bounce rate. So if we think about bounce rate, that's when somebody goes onto a website and then bounces off of it, the bounce rate increase probability goes from 1 to 3 seconds is 32%. So it's not too bad, not a horrible number, but if we go from 1 to 10 seconds, it's 123%. It's a massive difference. It's a massive cost that every second adds. So the technologies we're going to be talking about today is Next.js. If React is the library, say it with me, library, not a framework, then Next.js is the framework. Everyone here knows Next.js. It's nothing new. Nobody's heard of Next.js before? Should we start all over from scratch? I need engagement, you know? I have issues. I need crowd engagement, otherwise I can't continue with the talk. And then the next one is Tanstack Query. And I know you all had Dominic Dorfmeister talk like at the last edition, but weirdly enough, he didn't talk about Tanstack Query, so I'm gonna steal this. I actually gave this talk in front of him 2 weeks ago, which was a really interesting experience to be giving a Tanstack Query-esque talk in front of the dude that maintains it, but oh well. So Tanstack Query, if you haven't heard of it, it's a powerful asynchronous state management library. And I like to emphasize asynchronous state management library because I've seen so many code bases treat it as just like, I'm going to use it for fetching, and then I'm going to fetch something from it, I'm going to store it in Redux, and I'm going to store it in another global store, or something like that. It's a global store. It just so happens to be really good at all stuff asynchronous, and the main asynchronous stuff that we do is fetching. Next I want to talk about is API types. We deal with different types of APIs, one of them being, for example, public APIs. Has anyone ever used the Star Wars API before, the Pokemon API? Or gone on this GitHub repo of awesome public APIs, right? Some of them that don't require authentication. Maybe you've tried to like DDoS them or something like that, had a little bit of fun. But These are what I consider black box APIs. You have no control over them. You have no clue if they're going to be subject to breaking changes. So if you build an application around it, it may just not work, like my slides aren't right now. There we go. So it may be subject to breaking changes. So if you create an application that has a dependency on a public API, it doesn't necessarily have to abide by semantic versioning. It could just break one day and that's it, your application is not working. And so we have to have different considerations when we're dealing with black boxes or unknown entities or APIs. Then we also deal with internal APIs. Those are APIs where, let's say you're in a cross-functional or you're in a full-stack team, you've got back-end team and a front-end team, and your back-end team is developing an API for you to consume as a front-end team. You're an internal consumer of that API. There's no external consumer, which means that you can freestyle it. You don't have to abide by any particular schema of some sort that's going to be for large-scale compatibility. You don't even have to adhere to REST design principles. I've seen really weird APIs that do things a POST request should do, but instead in a GET request. But you can freestyle it. Nobody's telling you off for it. Probably don't even have authentication half the time on these internal APIs. So again, they have different considerations because they have different consumers. And then the last one, which is the most important one that we're going to talk about today, is what I like to call partner and product APIs. And this is where the API being built is also a product being sold externally. We can take the example of Stripe. Stripe builds an API that they probably use internally for their Stripe dashboard, and they also provide externally for us all to consume information from. And so that means that if an internal engineer at Stripe wants to be able to have a different interface to get data from for the Stripe dashboard, they can't just tell the team, hey, spin up a new API. They've got to probably use the same APIs that were being delivered to them that are also being given externally. And this is the same case I had to deal with at a fintech company when we were building an API-first product. We had to abide by deprecation policies, where if something was going to change, you had to wait 6 months and deprecate something, then roll out a new version. You really had to abide by semantic versioning or whatever was appropriate in the whole banking world, because EMI licenses are really dependent on this. EMI licenses are electronic money licenses, so you have to actually have legal, there are legal constraints in terms of your API's uptime and a bunch of other things, so you can't just willy-nilly change stuff. And then you have to really focus on widespread compatibility over internal optimization. Now, with all of this information in mind, we're going to put our tech lead hats on, and we're going to look at a Jira ticket. Do we love Jira tickets? No? Do we like linear more? Yeah, more Notion? Anybody use a TXT file? Anybody use OpenClaw to track their tickets now? Okay, so we have better versions than Jira. I'll switch this out for the next time, but let's say we got a Jira ticket, and we got to focus on it, right? So this Jira ticket says that our front-end team needs to design a dashboard chart that displays the distribution of birthdays for the top 5,000 users in the system. So if we're already thinking a little bit, okay, I need to show a chart of some sort, birthdays are relevant, 5,000 users. Okay, so what do I do next? I want to think of a data source. Where am I getting this information from? So the data is available via an API, which returns a list of users with all their data. Great. Are we happy? That's what we want. Yes. There we go, interaction. It works well, doesn't it? Cool. Limitation. The backend is unable to provide a new endpoint or data warehouse that returns the required data format. There's a limit of 1,000 users returned for each request. So, what do we start thinking? Aggregates. What do we do before we aggregate? We got to maybe fetch some things in parallel, right? Maybe let's look at an architecture diagram. It's a little bright now to wake you up. I did it on purpose. No dark mode for you guys. So we start with a user interface. And client side, we're on the client side. Let's say we're fetching in the best place possible, which is inside our use effects. And we are making 5 parallel API requests on the client side. What happens when you shoot off 5 API requests? You have a loading state because you want to tell the user that something is going on. So maybe you go to one of 2 states. An unhappy path. And so if the unhappy path happens, you may choose to persist the loading state. You're trying to do something to recover. And we implement a resilience pattern. And the typical one is a retry. And you may implement a custom retry function. Anyone here work on a code base where they have custom retry functions? Okay, cool. So there's still code bases that do that. You could either retry all of them or retry one that failed. And then you can go to the happy path, get the data back. I map the data to the way I want it. I set it in state. I render the UI. I'm so incredibly happy. But then maybe a React state changes of some sort. I trigger that use effect. I work at Cloudflare. I DDoS myself. And then we get to a place where the API says, 429. I'm receiving too many requests. Please, can I go on a break? I've worked for 16 hours straight. So we're not in a great place. But what does the code look like? So we have this function called use fetch data. I've seen a lot of companies that have this. Under the hood, it's doing that beautiful use effect thingy-mabob. That's the technical terminology. And over here, we're doing this get fake data asynchronous request, which is doing the 5 parallel requests under the hood. That's why we're passing the quantity. And then we get the data back. We're going to then map it into that birthday chart data we need. We set that data in state. Happy days. Should we look at a demo and see how that looks like? Yeah, there we go. There we go. Now we're getting energy. Cool. We're going to look at the demo. We're going to load things. This is the perfect time for me to take a sip of water. If it's going to load. Wait. Oh, there we go. 5 requests. Wonderful. Right? 13 seconds. And let's look at the data that we got back. So we click in, we got cell number, date of birth, we've got location, we've got street, we've got the coordinates of the person, time zone, we've got their password too, which is fantastic, their username, their SHA, we got the salt, we've got everything. So much power with all of that data. And I switched to dark mode and now we're doing all of those requests all over again, which is that lovely little state change that tends to be in our context providers. So we're in a great place. We're going to wait another 13 seconds for that. If you're really good at math, which I'm not, so I asked ChatGPT to help me calculate this number, the total payload of all those 5 requests is 1.58 megabytes. 80% of that was unused. So what are the key factors of this initial implementation? Let's look at our initial architecture and question it a little bit. Custom retry, it needs testing. That custom retry function, do you guys have unit tests for it? There we go. You need to maintain that thing. It's not just going to work magically. And it could have bugs. Have you ever found a bug in it? Okay, never mind. We didn't have this conversation. I trained him with cards before. So caching, we've got none by default. State, it's complex to manage globally and handle data staleness when things no longer become relevant. Data mapping, all the effort has to happen on the client side, and you may have to do potential memoization. Has anyone heard of use memo and use callback before? Has anyone seen that linting rule or ask Claude Code to write some code for you and you see 500 use memos all over the place? Yes? Do we just put them and we don't think? We close the laptop, we commit, or we ask Claude Code to, there we go. Yeah, that's generally the attitude. I have a whole talk just on use memos. Yeah, so we may have to do that effort on the client side. Payload's not optimized for state or for caching. And that brings us to sort of a magic number, 14. Has anyone ever heard of the 14 kilobyte rule? Fantastic. This is the one time I don't want any reactions. So great, everyone follow the memo. So 14 kilobytes fits within a single initial congestion window for a network request, minimizing round trips to the server. And I'm going to create a little diagram over here so we can visualize this. So if you're requesting a website from a server and it's within 14 kilobytes, it's just going to return that thing to you and be like, I'm happy, I'm going to render this. But if it's slightly larger, then what it's going to do is it has that initial congestion window. It's going to request the first 14 kilobytes. It's going to come back. It's going to acknowledge that it's going to go and request the rest of it. And then it's going to return the final kilobyte. And then it's happy. What's so interesting is that in certain cases, the difference between 13 and 14 kilobytes of a payload can be a couple of milliseconds, whereas the difference between 14 and 15 kilobytes can be like 500 milliseconds. But this 14 kilobyte rule is a little bit obsolete in wording because it comes from quite some time ago, but the principle still applies around your initial congestion window. And so sometimes for modern CDNs now, this is increased up to 46 kilobytes, and the number is sometimes hard to calculate, so it's different. You need to test this per provider. But what it helps us think about, again, is that initial congestion window and also the stall. The stall or the stall cost is this round trip that you have to make back to the server. I got the 14 kilobytes, I need the extra kilobyte, I need to make a round trip to the server. Just like, has anyone ever had that experience where like they've got a bunch of grocery bags and like I don't want to make extra round trips, so I'll put like 4 grocery bags here and another 4 here and they'll break along the way? Sometimes you have to be reasonable and make round trips with those grocery bags. This is the exact same thing. So this round trip depends on a user. And so on a LAN connection, it's 1 to 5 milliseconds. It's barely noticeable. Typical broadband, 30 to 70. 4G, 5G, 80 to 200 milliseconds. And in some places, there's still 3G being used. So it starts getting noticeable. And so what do we tell ourselves? We need to get our critical rendering payload under the initial congestion window. And this is where I like to introduce the backend for frontend pattern. And this is not a new pattern, but if you go on a backendforfrontendpattern.com or one of these websites, there are several ways to go about this pattern, but the one we're going to look at today is the transformation bridge or the aggregation proxy. And what's really great about it is that you can adapt it for platform requirements. So if you're building a TV application, mobile application, a web application, you can have a singular BFF serve multiple of them. You can decouple concerns, optimize for performance, make sure that you really have your separation of concerns at the BFF level, and you can optimize it however you want, so you can have separate parts of your team work on them. And then you can actually take whatever API you were consuming and then produce a structure that is actually for the final output you want to push to your components. So for our chart, we want to chart data for how many birthdays there are distributed in January, February, March, for 5,000 users. That's all the data we need. Let the BFF handle it. So like, what does an evolved architecture look like if we just add this proxy? So we're back at the user interface, the client side, but this time we make one API request to a Next.js API handler. We're in that same loading state, and the API handler does the exact same thing that the client side was doing before, where it makes 5 requests on the server side. Same story with the unhappy path around the retries and the failures, and around the happy path, you map the data on the server this time, you send it to the client, you set state, change to dark mode, you're back in a bit of a sticky situation. But what you've really changed over here is you've taken this mapping or the data that you were fetching over here and you've just pushed it so that you're fetching from the proxy itself. This looks like a really small change, but we're going to see how impactful this could be. So what does this do? This helps us isolate failure to a single client request rather than managing multiple of them. So you delegate that to the proxy. You have that code-based management that's a little bit easier with the separation of concerns. Your data is being mapped to the proxy level, so goodbye to your use memos. And the payload can finally be optimized to the minimum viable values. And this is so important because if we saw that original payload of 1.58 megabytes, if you were to cache that in local storage, depending on the browser, has 3 to 5 megabytes worth of local storage available, capacity available. So if you were to make more requests than just that, you'd run out of local storage very quickly. So you can optimize that at the caching level too. Should we look at a demo to see how that one switch made a difference? There we go, a bit more excitement. Cool. So we're going to load things again. We're making one request half the time. And we're doing the exact same thing under the hood. There's no server-side caching, nothing like that. This time around, we're just sending 300 bytes to the server. And so if we think about network bandwidth, actually, for that 1.58 megabyte payload, so what we were doing before, on a Wi-Fi connection, so 90 megabits per second, 340 milliseconds of download time is not too bad. On 4G, 700 milliseconds starts to get painful, but we're still within the initial user's flow of thought. 3G starts to get to 6.5 seconds, and that's unbearable. If we look at the network bandwidth calculations for the 300 bytes, which is what the second implementation shows us moving to the proxy, for Wi-Fi, 200 to 210 milliseconds. 4G, 200, 210 milliseconds. 3G, 200, 210 milliseconds. And we're going to look why. Why is that the case? And to understand that, you have to think a little bit in terms of ingress versus egress. So we're going to put our DevOps SRE hats on for a second. So ingress is data coming into a system or network. Egress is data coming out of a system or network. And so cloud providers are very happy to charge us for egress, but very happy for data to come into a network. So In terms of ingress and egress, you could operate it with two different types of models. So your function as a service is generally your Next.js API handlers. Those are your AWS Lambdas, your Vercel Edge functions, your Cloudflare workers. Those are subject to between 1 and 5 gigabits per second, but very hard to calculate ingress bandwidth. And your limitation factor here is you have cold start times between 100 milliseconds and 2 seconds, which impacts performance for a little bit, but then it just stays hot. Has anyone ever used like the free tier of certain like Heroku or like Netlify or whatever? Like something I used to do back in the day, which you probably should not do, is I had a Raspberry Pi just ping the thing to keep it hot, and then the bill went up. But yeah, that's one of the things there. And then there's infrastructure as a service, which is probably your Node.js microservices or whatever else, your larger backends, your monoliths. And those have slightly higher average ingress bandwidths, and those are your AWS EC2s, your GCP computes, and those are always running slightly more expensive, and the bandwidth tends to scale with the size. How am I doing on time? Do I have 5 minutes, 10 minutes? I need to know how much I want to rush it. Go on. I have carte blanche. I'm going to mess the whole schedule up. Cool. Oh God, I've started an issue. Cool. So TanStack Query, I'm not going to get into it too much. You can look at all the benefits of using it, but let's say we use it into this. We're slide 102 of 133. We're going to get there. So let's look at an evolved architecture and just planting TanStack Query into that. So we're at the user interface, we're at the client side. We're still making an API request on the client side, but this time React Query, TanStack Query is handling that for us, which means we're doing no loading states via our use states or our use reducers. We're letting React Query control that, and then the server is still doing the same thing, those 5 API requests on the proxy level, and then we can have an unhappy path where we return an error code, but this time having TanStack Query into the mix, our retries are a lot easier to handle because you can have standard retries or exponential backoff out of the box, which is really, really powerful. And exponential backoff allows you to essentially not retry immediately one after another. Instead, so it would work like, okay, request 1, 2, 3, 4, 5. Exponential backoff may work like request 1, I wait a second. Request 2, 2 seconds. 3, 3 seconds. And then you could add jitter to avoid thundering herd problems, which I won't get into. Then, if we're in a happy path, we map the data on the server, we send the data to the client, we cache it in memory the way TanStack Query handles it, derive the state from the response, we render the UI, and even if we mishandle the React state change and we go into dark mode because our eyes are so painfully hurting right now, TanStack Query is going to check the in-memory cache, we're going to get a cache hit, and it's going to render the UI. So it's even going to compensate for us mishandling our state. And if we have a cache miss because it's stale, we start the journey all over again. And so the way that's going to evolve that function we were using before is instead of what we were doing before with that use fetch data hook, we're going to use query. We're going to track them with query keys, which is really useful, especially if you're sending query params. But this is a whole other talk in itself in terms of how this works under the hood. Set a stale time, and you're making that request to the proxy. So what are the key factors here? We've now delegated to a third-party library to control the error handling, deriving the state, managing the cache. This is fantastic. And we've optimized now we can optimize with caching with multiple strategies. We can even do offline caching with local storage, IndexedDB, WebSQL. You have multiple options. You can a lot of plugins with TanStack Query. You limit re-renders because you limit refetches. And so you manage data staleness a lot better. You've got resilience patterns out of the box, which is really, really helpful because you don't have to always think about them, test them, maintain them. But we can go one step further. Let's say we start the journey on the server, and we're slowly getting towards the end. Let's say we start on the server. You have, let's say in the days of the pages router, you had that get server-side props where you can make a request on the server, and then you would send some stuff to the front end and pre-populate it, and then you wouldn't fetch on the front end. So let's say we start on the server, and we make one API request in that get server-side props, and we use a TanStack Query prefetch to handle this. What we're going to have is still that loading state, controlled by TanStack Query once we get to the client side, but what's really interesting is that you have another problem that happens when you come to the server, which is that if that request takes longer than 2 seconds, 3 seconds, 4 seconds, we're not sending any HTML to the client. We're rendering nothing, whereas in the previous case, where we're not doing any fetching on the server, we'd still send some initial HTML, can show some loading states, some interactivity while work is happening in the background. And so what you need to do when you have server-side requests is to set timeouts in place with your prefetches. where if you match the query keys of your prefetches to what your use queries are doing on the client side, you can technically bail the request on the server if it takes too long in the suboptimal condition. In the optimal one, it would resolve in maybe half a second and you would render instantaneously the UI. Or you bail at 1,000 milliseconds, you then ship all the HTML to the client and you start to recover and you start to reconcile against your query keys or your cache from the server and your cache on the front end. And so you have that whole story again about the unhappy path, and then the happy path looks quite similar. What this is going to change in terms of how we are managing our data fetching is, as I said in the get server-side props, we create a prefetch. This is now a wrapper I've created around a TAN-stack query prefetch. We pass 2.5 seconds is that threshold at what point we want to abandon the request. And we create something I'm calling an optional query. The longer version of this talk, we look into something called optional and critical queries, which are different ways to create prefetches, but we can talk about that later on if we want to, off the stage. Then what you do is the data comes back, you dehydrate that, you pass the props, and then they are sent to the client. And so what we're doing over here is reducing UI delay if we're prefetching the data, because there's no loading that happens if it happens in a suboptimal condition. We're sort of load balancing a little bit, reducing the client data load because we're balancing some network requests by making them on the server and other ones happening on the client. We have a data recovery strategy where if we try to pre-populate some stuff by fetching it on the server, but we fail to do so, we can reconcile that and recover that on the client. And let's look at demo 3 to wrap things up slowly. So this is the Zurich.js meetup website, and what I'm going to do is I'm going to go to demo 3. And it took a long time to switch. This is actually the case where I gave no timeout control to my prefetch on the server. Demo 4 actually gives me a 1-second timeout. So when the request took too long on the server, we actually bail early, and then we try to recover on the client side. So we're managing what's happening on both ends of the stack. And we land ourselves in a place where it actually just took 3.8 seconds to load. So what about real-world results? All of these were filmed on an airplane, on the way to React Summit, New York, and that was the network connection on the airline. So the reason that all those initial demos were slow, starting at 13 seconds, is we actually managed to optimize an application to render or get your data from 13, shaving down 10 seconds to 3-ish seconds on an airplane. Has anyone ever had a good time with airplane Wi-Fi? Now we know how to fix that. So instead of jumping through all of those engineering hoops, couldn't the backend have just made the damn endpoint? And it's not the point at the end of the day. The point is sometimes in startup teams, in teams with low resource, you have to be pragmatic. But also, it's time to be curious, not just delegate everything to your Claude Code or your ChatGPTs, and just get curious. How do these things work under the hood? How can I get creative with my solutions? And now I'll thank you for your time.